Okay, yeah, let's get started. So, it's exciting to have another AirLab summer school. We haven't had those last time was 2 years ago. So it's great to have this again. Um, and I'm actually really looking forward to it. Always have the chance to learn something new. So this just kind of a preliminary thing is if you haven't, please get the Matlab planning toolbox. And if you haven't installed Matlab, it might be too late because it's a 17 gigabyte download. Depending on your internet connection, that might take a while. But you can try it. So yeah, so make sure to have those ready. We'll need them in a little bit. So so the high level, for this tutorial week is to not really necessarily go into the latest and greatest, but be able to give you a good overview of the core ideas so that you can then know kind of what would be a baseline, what are the things you'd start with, where would you go, and so this session on planning is a lot on the basics, but it has some is a little more tailored towards flying, right? So we since a lot of what we do is kind of real-time mobile robots, or a lot of on flying, this is a little more heavily geared towards this. So, as you know, where we're trying to get to is to really solve some of these harder problems, and then kind of we spend a lot of effort on, how do we kind of go beyond the nominal problems in robotics, but this this is not what we'll kind of focus on in this talk. So basically trying to get from engineer in the loop, what we used to do a lot, to kind of an engineer on the loop. So let me give you two examples to kind of, these are a little older, but I think it might be fun to kind of get a historic perspective on how planning was done back then, and still done very similar right now. So this was 6 years ago, where we flew inside a ship that was on fire with a small drone. So here you can see the oil fire, and then it's kind of moving along. And so, in particular for us, what's interesting is how does the planning look like. So you'll see that I think next. So here you can see here's the map and the trajectory as it's being replanned. So those are so this is one example, kind of for the small robot side, and then here's kind of the other extreme, which is a large helicopter. So in the back here is the computing rack, front is the sensor head, and then the computing, the sensor head is actively steered to maximize information gathered. The systems kept safe. So you can see that in the upper right-hand corner here. It's kind of scanning out. Let's see a bit. So here, this green volume is basically the volume of cleared free space, and then the helicopter comes in, and then the sensor now is looking at the landing side, which is in the distance here. Make sure that the landing side, that the approach is clear, it modifies the trajectory, and comes in and lands. So you can see there's a lot of kind of planning components here terms of keeping it safe, modifying the paths. And so we'll talk a little bit about how that is done. So I'll skip the rest of the video. But so now that we've had the fun part of a couple of videos, so now let's get back to more on the planning side. And so typically we do this a bit interactive. So let's try and see if that works remotely as well. So here's some questions. So why don't we have one planning system that works well for everything?
One thing is that in different scenarios, you have different edge cases that have to be taken care of.
Yes, that's right.
System dynamics are different for different stones, so you gotta take care of different systems every time.
Right. Good. And then so, one thing that we think about is, what is, depending on what we want to do, what is common and what's different between these applications. And so, for example, in the two examples that I showed, like what's common and what's different.
There might be two different schemes where in one planning scenario you might want to explore more, whereas one you might want to prune more trajectories and get to the goal faster, if there's one goal.
Okay. What else is common and different?
It would have different possible trajectories because they have different different agilities.
Mm-hmm. That's right. Exactly. Other thing is one's much more constrained than the other one. And so what are potential ways you could try to figure out how to solve the planning problem? Yeah, so there are many different planning algorithms, and we'll talk about this and like maybe framed a little different than what you've seen before. So the other thing I wanted to kind of just put in context is, many people have heard about reinforcement learning, and just want to kind of give an idea of the relationship here between those. And so in reinforcement learning, you try to have some reward function, and essentially you're trying to come up with a policy that maximizes that reward. And sometimes, depending on the formulation, you have a model or not. And there's also this concept of a value function, which is essentially expected future reward. And so there's many different variations on deterministic, stochastic, and so on. And I don't want to get into the details, but just kind of want to give you an idea, kind of on the high level, where this fits. So, for example, one approach to this would be to essentially have a policy, could be a lookup table, which you could think about. For example, for Q learning, you have a lookup table which maps from your states to action to how much reward you get, and then you pick the maximum reward, and that's your policy. Now, what planning is about, you could also think about planning coming up with a policy, but instead of it being kind of a table or something like this, you typically try to reason about several future actions to come up with what your plan is, or often you might actually only execute a few actions before recomputing. Right, and so so you do need a model to try to predict how the environment will evolve. Your reward function is basically often also called the cost function. So it's kind of in some sense related there. And then the other thing you could think about is that often you can't really solve to the end, and so value function you think about like an endgame database or heuristic in some sense. So I hope that helped instead of being confusing. But the idea is that there is a relationship between them. And there's many iterations in terms of uncertainty and no uncertainty and so on. But in the deterministic case, you can think about it that way. So let's get into the details. So for example, one of the problems we often worry about is, okay, how do we get from A to B, avoid obstacles, optimize viewpoints, avoid no-fly zones, and land, for example. It's like a typical landing problem. And one of the things that's specific to what we often care about is the real-time part, right? So that changes the way you think about problems a little bit. So we might want to come up with this trajectory which stays in the Grand Canyon instead of trying to fly over. So for the rest of the talk, the assumptions here that there's little uncertainty, you don't have to do any exploration actions. And there are many variations on the problem that you can think about is, for example, you might not know exactly where you are, or you might have to sense before you can act, or you want to gather information about the world, or you might not even know what a better state is, so you don't even have a model. But in this case, we'll think about a more deterministic problem. So on the high level, what you really care about is, okay, how do we come up with this trajectory here and optimize the cost while respecting the constraints? And so the cost is typically consists of a bunch of functions. We'll talk more about these. Boundary value constraints would be you have a initial state that you start from, you have a final state that you're trying to get to, then you have some potentially have some non-holonomic constraints, and then you have some system limitations. And so you can think about this as a variant of the optimal control problem. And so one of the things that's kind of unique is that your cost function is usually only partially known, and you discover it on the fly as you go along. So just to kind of make it a little more specific, you imagine, so you have your start state, end state, and infinite set of trajectories you can choose. Your cost function here consists of the obstacles, and then, for example, a non-holonomic constraint that we often deal with is that you can't instantaneously, so that you have a non-holonomic constraint that you have to change direction before you can change your velocity vector. So it's like a unicycle model. And then an example system constraint is here, for example, a turn rate constraint. So what are some of the cost functions we care about? So one of the basic ones is the time to mission completion, so to get there as quickly as possible. Another one might be a no-fly zone, so this could be a polygon where it's essentially infinite or no cost, and sometimes we do some tricks to make things smoother. Another function is time to collision. So this essentially is a representation of collision risk. So if you fly faster, you want to give obstacles more clearance than when you fly slower. So what this basically comes down to is how long would it take you to hit an obstacle. And so there are some tricks to calculate this function quickly, because a typical, for example, distance transform representation will not allow you to actually calculate this correctly. And then, so you have some time to collision. Now, since the time to, if you keep on flying slower, your time to collision keeps on increasing. There's usually a minimum distance that where you still don't want to get closer to. So how do we represent obstacles? So one of the typical ways we do that is to say, okay, we have some sensor that measures obstacles. For us, LiDAR sensors or depth cameras are quite popular, but this model extends also to radar or some other sensors. So you get some measurement from your sensor that tells you, okay, here I've measured, for example, a range here, or here are the signal strengths for the different range buckets. And then you take that, feed it through a sensor model, and that gives you a probability of occupancy given the map, and then you update the evidence grid. And so the way, one of the ways we do that is to update this occupancy or evidence grid. And so each cell is assumed to be independent, which is not really a correct assumption, and there has been some work on trying to make that better. But for now, so you assume each cell is independent, and then you update the belief of that cell based on the sensor model. And so since you could imagine, let's say you had a relatively good sensor that at some distance you get many measurements of that, then your probability of there being an obstacle would go up quite a lot, and essentially a floating point number will run out of digits to represent that probability. So typically you use a log odds representation to represent the occupancy of a cell. And so that has a lot more resolution essentially at the edges. Now, many times we have very simple sensor models where we say, let's say at a range, the log odds that gets added is 100, and then anything before that decreases the likelihood of there being an obstacle by -1 or something like this, and so it update the log odds that way. But it actually can pay off to think about what the correct sensor model is. What is the beam divergence? Like, what is the how much does how many times are you going to see an obstacle at a certain range? And kind of really think about this. Especially for example, radar sensors, this can be quite helpful. Now, one thing that might be kind of worth just having in your mind about how does what we do typically work is, so imagine you had this robot kind of trying to go from A to B, so it starts down here, it goes in the upper right-hand corner. So initially it doesn't know anything. And so one of the things to keep in mind is that many times for planning, we make an optimistic assumption. where we say, if I don't know anything about the world, I'll essentially go straight and assume everything's clear. And then as you discover the world, so for example, here's a sensor, the evidence grid got updated, then you revise that plan. Now, this assumption of everything being free is actually many times not correct. And you know, there's some work trying to essentially extrapolate the world, trying to increase the planning horizon. But anyway, so here we've just sensed this obstacle. Now you'd apply some kind of obstacle expansion, and typically for a ground robot, you'd keep that relatively small because you want to kind of fit through quite narrow spaces, and there isn't really a lot of preference for staying away from things if you don't have to, as long as it's fine now. So let's say so now you keep on moving, see more, plan, see, and so on. So you have this, so this would be a typical cycle for a ground robot. Now for a flying robot, one of the big differences is that if you can stay away from things further, you would want to, because that would that allows you to fly faster, because you have, for example, more tracking error the faster you fly, and also increases your safety. And so now the other thing you can do is basically it's 3D, right? So what that means is that for a lot of these evidence grid and so on representations, the update of cost of updating, for example, the distance to the closest obstacle can be quite more expensive. Now, one other thing, and I just want to kind of hint at this without going into much detail, is that, you know, since you incrementally discover the world, is there a way to essentially completely incrementally replan? And there are some paradigms to do this. So, for example, you know, imagine you had this evidence grid. As you update it, you keep track of what changed, so you get a list of updated obstacle classifications. Those updated obstacle classifications, now you can actually incrementally update your cost map, and then with an, for example, incremental distance transform, and then from there you get an updated list of cell costs. And now these updated list of cell costs go to an incremental planning algorithm like D-star, and now you come up with a new plan. So this actually allows you to plan very quickly and completely incrementally at no computation. Now, one of the things that we also sometimes run into, and this is just a small trick I want to mention, is that, you know, if you fly, for example, at you know, 60 meters per second over long missions, like this would be for the large helicopter, but we have similar problems kind of on a scaled down version with higher resolution. You can't keep a big grid in memory, and so one of the ways you can just do it is to scroll the grid, and that's basically, it's like a scrolling ring buffer. So just want to mention that. Oops. So so now I want to kind of open it up for some questions that you might have, but also maybe those are two questions that I'd like to ask you. So, for example, what are some of the pros and cons of this type of evidence grid filtering? So when would you when would you use this filtering, and when might you not want to use this? Oh, okay, I got a message here. Okay. Yes, okay, performance of the planner can depend on the resolution of grid and requires tuning and size resolution for specific application. That's true. What are some alternative approaches to represent the world, and what are their advantages and disadvantages?
Let's say, so like one alternative is, and I recently saw a paper about this from UPenn, where they were detecting trees, like they were flying in a forest, and they were saying, okay, here's like my trees, and then these are my obstacles. And so then when they would do collision checking, they were just checking to see, like, are they, you know, within these trees, basically, right? Like, is my path within a tree? And one advantage to that might be, like, if you don't expect any other types of obstacles, you might have like a better time detecting like the things you expect to see, and then like avoiding those. But the disadvantage is that, you know, it might be more computationally expensive to, you know, detect a tree and then determine, you know, is my path like within that tree or not.
Okay. And so what do you think the pro and con compared to, let's say, an evidence grid would be for this, or like a distance transform?
The pro might be if like you have a very sparse environment, for example, and you only expect to have like, let's say like you're on a racetrack, for example, and you're like a race car, you can detect individual cars and then do prediction on like where you expect the cars to be, right? And so then you can say, okay, I'm going to represent my world as this list of cars, and here's how fast they're moving. And so then you can do like additional like checks to see, okay, is this point in trajectory in time, is this going to avoid the car at that point in time? Versus if you just had like an evidence grid, there's directly in like a 2D grid, there's no time component, right? Unless you do like some kind of like inflations or whatever. So you would have to have like multiple grids, or you would have to have like a 3D grid that also has a time component for each cell, in order to be able to do any kind of like future collision avoidance with time.
Okay. So let's see. So there's now some chat message. So Alice, do you want to expand on what you wrote?
I don't have too much experience with it, but I did see a paper or like some work being done by Dr. Case on Gaussian process implicit surfaces. So it's like a continuous representation of the world just by using Gaussian processes instead. And it's supposedly like very memory inefficient, but I guess the downside of that is like you have to compute the distance function like all the time.
So okay, a Gaussian process. So yeah, that could also be an option. And then, so Jay had a question on distance transform get prohibitively expensive. So this is, so if you're in this incremental paradigm, not necessarily the size doesn't really matter as much as how many cells change. There's a certain number of cells per second in some sense that you can change, right? So if your map changes, like if you fly very fast, for example, and your map changes a lot, then you might not be able to keep up with updating that map. Now the part that's most expensive for an incremental distance transform is actually not adding new data is relatively fast. It's if the classification of a cell changes from occupied to free, because now you essentially have to go through the region twice, right? So you have to go so if you remove a cell, there's now this kind of area that's painted in, that has some distances. That's wrong now. Now you remove that, so you have to essentially clear out all the cells, and then you have to go in and fix all the cells. So that part is the most expensive part for the incremental distance transform, is basically flipping a cell from occupied to free. Now we did, for example, for this helicopter work, we did do this kind of in a scrolling grid fashion, incremental distance transform at 60 meters per second over a grid that is a couple of kilometers. So it is possible to do this. But there's some parallelization tricks also. Now another representation would be a mesh, for example. Yuheng, do you wanna maybe give an idea of what might be some pros, cons for this?
Well, actually, I'm more familiar with the SLAM topic. So when I'm thinking of the representation of an obstacle, I think maybe you can get some more precise or focus more on the boundary of the obstacle. Maybe just using the point and line feature can be enough. In this case, we don't need the grid to fill all the space. Well, just thinking. Yep.
Okay. So what about point clouds?
I think point cloud is quite similar to the grid, maybe. You can just fill the space with point cloud with the grid. So I think they might be the same.
Yeah, so I think one of the advantages of grid over point cloud in certain situations is the ability to filter out noise. So you can, if you get false positive points, for example, in a grid, you can filter them out to some extent, while in a point cloud, it's a little more difficult to do. But it's just, right? So this is one, it depends a bit on the sensor, right? If you have a laser sensor and you don't expect to see a lot of dust or something rain or leaves, and just a point cloud might work okay. But it also then, how do you do the collision checking quickly becomes a kind of a separate question, separate data structure question.
Do you mean that because in a grid, because you're maintaining the data structure over time, you can sort of compare over time if a noisy point that was thought to be not free goes away?
Right. So when you do this updating, you essentially, so you have a sensor model. So you have the sensor model, and so you start out with unknown initially, depending on, and this depends on the quality of your sensor. Often we have very high quality sensors, so we don't have to do a lot of work. But imagine you had a sonar or some kind of noisy radar, right? Like initially you might have only a very smeared understanding of where obstacles are, and only by filtering those measurements together you can get a sharper picture. And so, or you could imagine you would see some dust here in one of these measurements, and you had seen before that it's free, this area, then just because you had one point that has dust in it might not affect your grid. Okay, cool. So now, so we talked about cost functions. So another part of it is essentially our model of how do the dynamics evolve. And so one model that we often look at for faster flying is coordinated turns with no side slip. So I just want to kind of put these equations up here. As I don't want to go in details. You can just look at these for reference. Wind you can think about as pushing you in a constant air mass. I'm not really thinking about wind right now. And then I just want to kind of keep these up here. If you ever have to implement this, can be useful. So those are the coordinated turn equations. Gives you a fast way to integrate it with essentially a big delta t. Okay. So now we have this problem. We have our, we know how the dynamics evolve. We have our constraints. We have our objectives. So now we have some limited amount of time, and that depends on the problem a little bit. It might be 100 milliseconds. It might be a couple of seconds where we have to come up with the best trajectory. And so, since we are in a computer, we basically have to discretize that problem. And so one way to think about this, once we start discretizing this, is to essentially think about the problem as a graph instead of continuous space. And so we'll kind of think about that problem. So now, a lot of what we had goes away, and we really have to really just think about this graph. And we often don't explicitly construct this graph, it's more implicit, but there is usually an underlying graph. So we have the start goal, and we want to find some kind of path through there. Now, so how do we define an edge is what we have to think about. And then what do we do with our objectives? And so once we have, the nodes, the edges, then really we just have to find the best path through the graph. So, edge costs, cost between two nodes, and cost depends on the objective J of the trajectory segment, and calculating that cost can often be expensive, and that's typically due to collision checking, because you basically have to check, hey, does this edge between these 2 points, is that a valid edge? And so to find the least cost path, we have to calculate the cost to go, and then basically can go backwards from the end and find the best way to. So we calculate the cost to go, and then to find the path, we backtrack to get the actual path based on the best predecessors. Now, the main questions. So this is, essentially the general problem of essentially searching a graph. Now, the problem that we have to deal with a lot is we have a fixed time, we have fixed memory, and so we can't really solve the optimal problem. So we have to think about, because there's an infinite choice of essentially where we put vertices and edges. So we have to think about, like, where do we put these vertices, and where do we search? And so that's what a lot of kind of motion planning really comes down to. And so I want to look at three representative approaches that look kind of very different, but you could think about them in the same paradigm. So one of them is regular graph search, so A-star grid search. I want a sampling-based approach, T-star, and then trajectory optimization, and we'll use CHOMP as the algorithm for that. So, and I think a lot of you are familiar with A-star probably, so there are two parts to A-star, and essentially one is the optimal. So you have the G value, which is the cost of the best path from the start. And then you have your heuristic H, which is an underestimate of the cost to go. And then, so you think about our two questions. What vertices do you create, right? So if you think about more as an implicit graph construction, you pull your vertices from based on your heuristic and G plus H. And then where do you search is basically look at the priority queue in your A star to pick the next vertex to look at. One popular function for heuristic is Euclidean distance, but there are many. There's a whole line of research just trying to come up with good heuristics, but it's not going into this. For heuristic to be admissible, it has to be an underestimate of the cost to go, and it has to be consistent. And so what that means is it has to satisfy the triangle inequality, which means that if you, like on the high level, the idea would be that if you have some detour that can't be lower cost than the other, the direct way. So the search is, and we're going through this quite quickly, but so you start at the start, you initialize, let's say you have this explicit graph, right? So you start at your G value at the start is 0, so just a backward search, and then any other value is infinite. You add your start vertex to the queue. Oh, this is I guess this is forward search. Yes, forward search. And then you pick your lowest cost vertex, so your lowest G plus H vertex from the open list, expand it, so you look at what are the neighbors, calculate their cost, update the values, add them to the queue, and keep on going. So A star is resolution complete and optimal, and it will have the minimum number of state expansions. Now, the kind of questions that you have to think about is, what graph should you create? And the standard thing to think about is like a 4-8 connected grid, but there are many different ways to create a graph. And I think one of the things that I already kind of brought up with the grid mapping part is, the resolution matters, right? Like if your resolution is too fine, you might spend a lot of time on searching something that's irrelevant. If it's too coarse, you might miss a path. And then the expansion also depends, depending on how expensive it is to calculate costs, you can play some tricks in terms of how you actually calculate the cost functions to try to avoid calculating the whole cost. And and so getting a good performance, depends a lot on your branching factor and the quality of your heuristic. So if you have an uninformative heuristic, you essentially have to search the whole graph. And if you have a high branching factor, that can make things much worse. And so this match of the graph abstraction to the environment basically means if you have, how many invalid edges will you have, right? Like if you have a lot of invalid edges, then it's very general, but then you have to invalidate a lot of edges when you're doing expressions. So here's some links, if you want to kind of go down further into this direction. The references are at the end. So one idea to think about is imagine you had you didn't want to have a regular grid, but you want to have a grid that has dynamics in it. Then you can think about something like a state lattice, which is a repeating structure over your so you look at the dynamics and then you create essentially a grid-like structure, a repeating structure that you can search that takes the dynamics into account. There are some subtleties with this in terms of making it high performance, but that's one idea. And the advantage of having this repeating structure is that you can actually recognize when you come back to the same location again, to the same state again. If you have something like a search where you just keep on expanding, and even if you end up in almost the same state, you might have a different vertex and you don't actually know that you come back to almost the same state. Maneuver automaton is a slightly different idea where you essentially create a finite state machine that's a discretization of the different states you could have, the different commands you could execute, and then you can essentially search over that sequence of states in the automaton. Instead of just straight lines, you have different heuristics. And then the other kind of direction that you can mention in the beginning a little bit already is, what if you don't want to redo the search every time? What if you want to use prior results from our search? So I'll maybe stop, take a quick stop here just to give you a chance to ask some questions.
What does resolution complete mean?
So resolution complete means that so you have to pick some discretization of your graph. And so within that graph, so let's say, easy way to think of it is imagine you're searching over a regular grid, like a chessboard, right? And your chessboard will have some resolution, let's say 1 meter or 10 centimeters. And so then in that resolution, you will visit you can generate all the solutions in there. But if a solution requires a decision that's a 5 centimeter step size, then you can't find that. So it's complete in the sense that it searches everything up to that resolution.
One question came up in the learning physics project is that so normally the search-based method often represents the node as a node in a 3D or 2D space. So what if we have more complex states, like we want to incorporate the velocity and the relation between the robot and the obstacles into the state? Is there any work on?
Yes, I mean, if you want to essentially increase the dimensionality, there are a couple of other tricks and problems you run into. So, as you increase your dimensionality, that essentially means you also increase your branching factor. And so the higher your branching factor goes, that will really slow down your search. Now, the other thing you run into is that your heuristics might be less informative. And so essentially now you're in a situation where you have, I don't know, hundreds of potential at each state, hundreds of potential next states you could look at, and you don't really have any clue on which direction you want to go in. So then that really can slow down that kind of approach. And so that's where some of the ideas then people look at. So for example, for manipulation planning and so on, is try to maybe first plan in a lower dimensional space to get some good heuristic, or if you can solve it without looking at the full state, then you do that. And then only in the situations, for example, let's say the door, we have to like fold your arm in, then it starts searching in the full space where you have to look at that. And then the other thing that is essentially this, let's say, state lattice or maneuver automaton idea, where you say, okay, I'm restricting myself to a certain set of potential actions, or essentially actions to create a smaller graph.
Yeah. So a follow-up question would be, so we know there's in the manipulation task, like for a 6-degree or 7-degree of freedom arm, people can still do search-based method. So what is the reasonable or maximum dimension we could do this search-based algorithm before it goes too time consuming?
It's an interesting, but well, a lot of it comes, I mean, when you do this kind of 6-7 dimensional planning with a search method, that often, to do it in a reasonable amount of time, that often means that you have some good heuristics, so that you can really guide the search and keep it in a region that doesn't explore not so useful areas of the state space. Now, the other thing for manipulation often is that the time scale is also a little bit different, right? Like, for example, we're looking on the order of hundreds of milliseconds, or maybe a couple of seconds, versus maybe minutes for manipulation planning. So, yeah, I mean, I think anything like 6-7 dimension that starts pushing it, I think that's, once you start going beyond, I think like 8, 10, then definitely that's where these types of methods might not be the best choice. And
Okay.
so actually that might be a good transition to next topic. so and so that's actually where a lot of the sampling based planning came from, is trying to solve these high dimensional problems. So from our context, what the problem is, we don't know often where we should put our graph and what resolution to pick, right? Like, we might want some higher resolution, some coarser resolution, and if you have some kind of like a fixed resolution graph, then it might be resolution complete and optimal on that graph, but you don't necessarily know what the graph is. And so the idea for a lot of sampling, for sampling-based planning methods, is to sample the environment in an increasingly denser fashion, and then connect the samples to construct a tree to find a path to the goal. So this is for our T-star. Now, there's some different methods like road maps and other methods, but initially, actually, those methods came from the manipulation for me where it's like, okay, let's just find any solution by sampling in this 10-dimensional space to find some arm. But now more recently, those methods are also useful for lower dimensional problems. So we can think about this kind of in a graph fashion again. So initially we have a start and goal vertex, and then we sample potential locations to expand to. Now, there are many ways to do the sampling, and there's a lot of the whole kind of thread of research on how to find the best samples. You can sample uniformly, or you can try to sample biased based on being between a start and goal, or not being in low-cost areas. So there's a lot of kind of ways to do this. But so let's say we just sample uniformly, we add a sample, and then now we add an edge to connect to the graph. And so that's called the expand state. And there are several ways to do this. You can typically you try to actually go to that location you sampled from and add it. Sometimes you only go a little distance, and then so then you keep on going, and every time you pick some sample, you find the closest vertex and then add it to your tree. Now, one of the interesting kind of things that happened, there was an algorithm called RRT, and that's exactly what it did. And so you could actually show that that would not necessarily create the lowest cost. It would be, you can prove that it is suboptimal. And so the one of the problems is that essentially you can have these unnecessary detours where you kind of, as you went along, you can build up your path, but then you'd really have to make the best path, you'd actually have to change your connections, and the algorithm won't be able to do this. So RRT is a little different in that it has this rewire operation, and so we'll go a little bit over this. So when you add this new vertex, one of the steps you look at is this, it's called rewiring. So you look at your neighbors within some radius, and that radius has a certain way it decreases that you can show that it's will almost surely converge to the optimal. And so here there are two neighbors, and so S4 is actually the better neighbor. And then now you check if there are any outgoing edges that have a lower cost. So here, actually, if you connect S3 to S new, that path is lower cost than going from via S1, S2 to S3. And so now you do this rewiring by changing the parent and then fixing the tree. And so I don't want to get into too many details, since we're trying to keep this as an overview, but the idea is so you get a sample, you look at all the vertices within this radius, get the best neighbor, add that connection, and then you do the rewiring. Now there's actually some interesting theory behind how that radius decreases over time, and it's something to think about. But the idea is that it's on the high level, you think about that you just kind of want to, as your graph gets denser, you kind of want to shrink what you look at. But there's some good thinking behind this. So why do we want to rewire the tree? So we want to remove these unnecessary detours, and what that does is it will optimize for the minimum cost, rather than if you just grow the tree, that you're essentially committing to these edges too early before you have really figured out what the right connection is. So here's some questions. So what's expensive about RT stuff?
Is this searching inside the radius part?
Can you say that again, Yago?
Is this the searching inside the radius part?
Yes. So inside the radius means you essentially have to find the nearest neighbors, right? So that part is expensive. And so that basically means that rewiring step is expensive, right? Without the rewiring step, I guess so without rewiring step, you only have to do the find nearest neighbor once to essentially, when you pick a sample, hey, what's the closest point that I should expand from? So that part is expensive. But then for the rewiring, you have to find the n nearest neighbors within a radius, and then do this whole rewiring, which is expensive. Okay, so then, so let's say the second question. So if we have, let's say, kind of our helicopter that's motion constrained and so on. So is this R still optimal? So one thing and I can maybe go back a little bit, think about it. So when here what we do is, so we look inside a radius, what are all the closest neighbors, and look at all of them. Now actually, if we have a helicopter, for example, let's say flying, let's say this direction, none of the vertices that we find in the back, will kind of go check, but we'll never actually make use of them, right? So there's this definition of the radius is actually only valid or really relevant if you can go any direction. But if there's some kind of limit on the space rate of valid future states, then you'd actually want to change that definition. How can one incorporate heuristics? I think I'll kind of hold off on this a little bit, because I think Brady and Jay will probably talk about this in the next planning part. And then, so in what environments do you think this algorithm will perform well?
It won't perform well in, like, if you have like a very narrow hallway, for example, because you might not sample points along inside that hallway, and so then like it'd be more difficult to force the path to go down inside there. If like say like you have just like a small door that you need to get through. So it probably would work well if you have like a more open environment, where one where there could be multiple paths from start to goal. Like if there's not just one, valley that you have to go through.
Okay, good. Yes, exactly. So it won't perform well if you're essentially sampling lots of invalid edges, right? And then you have to check a bunch of edges that you can't connect to. But if it's, for example, very open, it will very quickly find a path, but then it will also have trouble avoiding unnecessary detours. But yes. So if you want to go deeper, why does this particular choice of R lead to optimal plans? You can look at Karaman, and then one thing. So we'll talk bit more about this one, I think. So that's bit star as a second question. So if you essentially have a batch of samples instead of and a heuristic. And then the third one is, now one of the interesting properties of RT star is that it optimizes to find the minimum cost path as quickly as possible at the cost of not having alternatives. So if you want to find a second best path, RT star will actively cut off solutions. So if you want to have a spread of good paths instead of just the best path, there can be some issues. So that's like the third paper. So here's just some idea that we looked at is, so one of the things, for example, you can think about is collision checking is expensive, right? So if you could just check some edge and then say which edges are likely to be in collisions and which not, right? So for example, here, imagine you're going straight at a wire and then now you have to check a bunch of edges to figure out which is the best path. Here's an idea where you basically just check a couple of samples. You can see these red lines. These are samples that are checked to figure out where potential obstacles could be based on some assumption about the environment, right? So you basically sample environments, and then anytime you find an edge, you basically will change your likelihood of an edge being in collision, and so you can very quickly find it. Right? So this is like one idea of how you can handle some of these problems. Okay, so the third idea is trajectory optimization, and we'll kind of talk about this more in the I want to talk about this more in the context essentially of a graph idea, because for all of these things, since we have this limited time and we have to discretize if you think about it that way. So for trajectory optimization, the idea is really to try to exploit more than zeroth order information. So you could think about a lot of the previous approaches like A star and RT star as taking a shot in the dark, right? Like you basically pick some random configuration, check, hey, is this good or not, or is this better? And then if yes, keep it. If not, maybe move on, right? But for the types of problems we look at, often our cost functions are smooth, right? Or we can make them smooth. And if they are smooth, then the cost function can tell us more than if it's good or bad. They can actually tell us the direction of where which directions will things get better and which direction will they become worse. And so trajectory optimization methods try to exploit that. And so for this particular method, we have, for example, an initial guess. So in this example, if you're on the right, you have a straight line, and then you optimize this over several steps. And so if you think about this from a graph example, you could think about, we have a start end. Our initial guess is the straight line. And then we look at these, look at the objective function, apply the gradients, add new vertices based on that gradients. And so we can keep iterating until convergence. Now, often we want the cost function to be smooth, so our robot can execute it. And we want to avoid obstacles. So that's the kind of example we'll look at here. And so the key idea behind CHOMP is to try to update the trajectory with a smooth perturbation of the trajectory. So, for example, you want to minimize the amount of velocity and acceleration added. And so the idea is to do steepest descent in trajectory space. And so for us, we look at trajectories, but you could have different parameterizations of what your commands are. So here is one example. So this difference in trajectory space is you can, so let's see, go back here. So this M matrix, so you take the, so the new trajectory is the old trajectory minus some update. So these are your gradients, and then M is essentially the matrix of how you apply those gradients to your trajectory. And so as you can see, it's the M here, and I'll kind of expand on this. So M is measuring difference in trajectory space. And so here is the final difference between waypoints. And so if you think about the example we had before, so on this initial straight line, right, you have two sets of gradients that show up. And they'll have positive as purple, green as negative, and so yellow as negative, and turquoise is 0. And so then when we take this final difference matrix and take the inverse, it essentially spreads the, if you multiply the GK by M inverse, it will distribute those gradients along the trajectory. So here you can see that after multiplying this, there's no change in X, because all the points still lie along it, and all your gradients kind of point up here. Or and so now you're smoothly changing that trajectory in X and Y, and so you keep on repeating this until convergence. Now, one thing I want to mention here is that we look at, often we use this in trajectory space, but you can actually use this in command space as well. Like if you had a, let's say you have a dynamic system, you want to come up with, let's say some U, like I don't know, some acceleration commands or turn rates or something like this. You could do that as well. So I guess one question is this method complete and optimal? So the answer is no, since it's an optimization method. And then the second question is, how could you include dynamic constraints in the trajectories?
Can you add smoothness of the trajectory as an additional cost, considering the dynamics of the underlying robot?
Yes, so you can add the smoothness. So there's basically kind of 3 ways you can have this. So the trajectory is already smooth through the update rule. You can additionally add like a smoothness function. But then the other thing is you can add constraints just by projecting the trajectory, keeping the trajectory, projecting the trajectory onto the set of feasible trajectories, right? So if an update will push you outside of a feasible region, then if you start inside, it pushes you outside, then you basically just project it back into the feasible set to make sure that you respect the constraints. There's another approach where after you've calculated this update, you apply this update to a dynamic model, which basically, so these now are actually changes in the commands, changes to the commands. You execute the commands, and then you have your constraints in there as well. So you basically can just have the dynamics in the loop for this as well. So that's just something to think about. Why is it an effective method for air vehicles? So it's useful for us because often we have a lot of free space, right? So you might have some obstacle. We kind of push things away from that to make sure that it's safe. And if you can push things further, then it's even better. So that's why it's a useful method. Yes.
So isn't it also effective for air vehicles because you can move in any, like say if you have a drone, you can move in any direction. Like if you had constraints on like the way you can turn and stuff, wouldn't you have to also consider that?
Yes, but you can include, like I mentioned, you can add that to the method. So right now this what we showed is basically just modifying the trajectory and then using that trajectory as the command, but you don't actually have to use a trajectory as a command. It can be commanding any dynamic system, and you can actually have the dynamics in the loop now. And it's not CHOMP per se anymore, but you can basically have this kind of trajectory optimization with the dynamics in the loop as well. But this method actually works well for kind of turn rate constrained vehicles as well, because it smoothly modifies the command, so it tries to minimize that deviation. And then, so how could you include other planning approaches in the optimization? And so I think we'll kind of hold off on this a little bit because we'll hear more about this later. So going a little deeper, like how do we enforce constraints on the trajectory? One approach is to project back along the same space. So imagine you exceed some joint limits, or you were trying to turn too hard, you basically just project the trajectory back. You can hear some other approaches on how to, for bigger, more challenging situations. Or here's another approach from a while ago, but I think it's still valid. It's essentially more of a quadratic programming approach to trajectory optimization. And then how do you combine this with RT-star? And that's, I'll skip this part because we're also kind of running out of time. We'll kind of talk more about this later. Now, I want to talk about this idea a little bit, because I think it's going to be important for you for the planning coding session. So, so for this autonomous helicopter, what we implemented is essentially this idea of, so you have this planning problem, and this planning problem in some sense is independent of the solution. And then we had a set of algorithms running in parallel, competing for the solution, plus this kind of end game library, which essentially, for some certain problems, essentially landing gives us, once you're within a certain region of it, it tells you exactly how to get to the end. And then a dynamics filter, which smooths out the solution, and then this kind of safety system. So just to kind of give you a high-level idea of how this works, imagine we have the same situation, an obstacle, sense it, now maps updated. Now we have our controller look-ahead point we plan from, we have the goal, and now we're running a bunch of planning algorithms. Each one of them gives us a different answer, and then we pick one, and then we maintain the old solutions and try to repair them. And if something would pop up in Planner 2, we still have Planner 1 and 3's results. We could switch to those immediately. And then, so that kind of makes the solution a little more robust. So here's an example. So we have several routes. We select one. And so here you can see there's, like, for example, this is the CHOMP output, this is the RT-star output, in this situation, our T star is more robust. Now it gets picked, and then so eventually now here the optimizer works better. So it basically keeps on switching back and forth between the different solutions. And you're basically part of the problem that we're trying to address here is that we have a limited amount of time and we have to pick where we place our samples and evaluate our solutions, right? And where that is better depends on the environment. And so, but basically you can show that if you want to optimally picking which planner to execute is as hard as planning itself. So you essentially, so that's why we're gonna have this ensemble of different algorithms that run in parallel. Now, one last idea I just want to kind of go over that might be a useful idea for some of your research is this idea of a dynamics filter. And so the idea is that you give it a partially feasible trajectory and then filter it to be fully dynamic feasible. And so, you know, often you have some system that has nonlinear constraints and you don't have an analytic solution, but you can essentially bound the maximum deviation that your filter would deviate from. And so as long as you deviate from it away from obstacles by more than that, you can still come up with a feasible output. So that's just some idea that might be useful in the future. So I think I'll maybe, let's see, we have, yeah, I'll just show a couple of results. So that was kind of the tough part of the talk. I think now just have a couple of fun videos. Yeah, I'll have to skip a couple of things. So any questions before I can move further? Okay, so let me just show you some fun old videos you might have not seen. So this is on board of the helicopter. You know, we fly. This was actually the result we got here was kind of an accident because they accidentally planned a path through a mountain because they didn't actually want to test this, but it happened that it, you know, and they just let it go in this case, and it worked quite well. So here we're going towards a mountain, we're evaluating the time to collision, observing the trajectory, and then so you can see it's kind of moving around the mountain. Now the scale is a little deceptive here. You know, it starts seeing those mountains about 1.5 kilometers out, and then now it's kind of flying around the mountain here. So you can kind of see here how the gradient gets applied to the trajectory, right? So based on the time to collision. So, you know, once it's past the obstacle, there isn't really any gradient anymore. So it's just in front where it happens. And so that time to collision gradient basically gets applied to the trajectory. Now in this example, you can also kind of see this idea of why you want to have multiple planners. Well, so you know, this blue line kind of shows you the cost, and then the different T-star AI's alternate route. So this is the kind of planner we had that comes up with multiple different solutions rather than trying to just find the best one. So yeah, basically you get close to the best solution, but you don't hit the best solution. And then the optimizer can really essentially take a couple of steps and find the minimum in this situation. Now, but you can also see where we had the situation where there actually is a no-fly zone right next to the mountain. And so in this situation, basically the trajectory optimization has trouble finding a path through the gap, but RT star can make a reason better about it. So and so in this situation, an RT star is picked. So you can see that there is an interplay between these different methods. So one last idea that I just want to briefly talk about, and we've already talked about a lot of things. Maybe I'll stop after this, and there's more stuff in the slides. Maybe I will talk about it in a different talk. Is this idea of the emergency maneuver library, and so you can think about this really as a generalization of stopping distance. So you want to have your robot be safe. You want to always have an option that that you can fall back on, where you can guarantee that the robot will not hit anything. And so what we're trying to do here is essentially, we know we have a cleared area, which is the yellow area. So this area is known free. We have known obstacles, and then we have unknown. And we want to make sure that our safe trajectory is always in the known free area. And so, yeah, I'll skip this part. So here's an idea, like a more of a pictorial example. So we're clearing this space. Let's say 3 trajectories. One is like a stopping trajectory. One's the left loiter, one's the right loiter. So as we move towards obstacles, maybe these 2 now are bad. The left one is not inside the known space, so that one's bad. And here we are actually heading towards an obstacle, and so the right one's still clear. So this means you can still fly without having to slow down, right? So, but you're still safe. So that's kind of the idea for this, so that you don't have to be overly conservative. And it can actually also lead to making your system more robust. So here, you essentially have some occlusion of, there's like a mountain here, but you can't see it because your sensors are occluded. So you plan through this because you're optimistic. Then at some point, the emergency maneuver gets executed because the system doesn't know what to do anymore. And then as it starts turning, your optimization, for example, is to find a path. Here's kind of a picture from the same video before. You can see there's all the emergency maneuvers, and you can see that as we get close to the mountain, these get cut off, but there are plenty of other choices left, so the system doesn't have to slow down. And so I'll kind of skip these next results. They're kind of fun to talk about, but I think we're running a little low on time. So the only thing that might be worth, yeah, I'll just talk about this part. So for this large-scale helicopter example, so you can see here, like often we were landing at across tree lines, and so there, this kind of trajectory optimization works quite well, because you have this kind of one-sided problem where you have obstacles, and you just kind of want to push the trajectory up a bit. For these large plans with mountains, these kind of random graphs are better. And then for kind of urban situations, kind of a state lattice can be quite better choice. But I'll skip some of these details here that are interesting, I think, but I'll talk about them some other time. Okay, so any questions for this? So I'll just go over the summary, then maybe we'll do questions, and then. So we talked about the kind of 3 different planning approaches: the A-star, RT-star, and CHOMP, and then also talked about kind of defining a planning problem. And it's really, you really start with defining your problem, and then you should look for an approach that can optimize your solution. Right? And since we typically deal with a kind of incremental discovery of our objective function and time limitation, which approach is successful depends a lot on the environment and the dynamical system that we are actually controlling. And so I'll kind of stop here and take some questions before we get to the planning toolbox.
Hey, Basti.
Yeah.
I had a question on, so you mentioned Ensemble. How do you think, what is your intuition on how this applies to, for example, like ground vehicles, like autonomous cars where there's a lot of dynamic pedestrians? Do you think there's a particular like planning approach that it's good for, and do you see that there's like canonical scenarios where there's like where we need this sort of ensemble method?
Yeah, so I think for ground vehicle, so for autonomous driving, the situation is a little different because the problem is more structured, right? So you have, essentially you want to try to stay in a lane with, and then maybe deviate from that lane a little bit, or stop, like on a regular road. Or then you have kind of this turn situation, and it's relatively straightforward for you to kind of classify these different situations, right? So for autonomous driving, you might have essentially like a parking lot, maybe intersection and road or something like this. And so, for a parking lot, you'd want a very different planning algorithm. Let's say you might want to use some kind of RT star. And then for on-road, you might want to use some kind of CHOMP with optimization maybe, or like a library with optimization maybe, an intersection and so on. So you can manually kind of pick which one you want to use, but it's still, from a robustness perspective, you might still want to run a couple of choices, even if you have one that works in 95% of the cases. So for flying, it's a little different because it's hard for us to kind of say what situation you're in, and there's many situations where you might not really know which one works better, right? So the idea is that it could be, for example, one of the things we saw for the helicopter was that maybe 90% of the cases, CHOMP would solve the problem well enough that we could use it. But there's still kind of 10% of the situations where it doesn't solve it. And so if you have another planner, then that can help pick up the slack. And then there's a lot more kind of on this ensemble work where you could think about that. If you run multiple things in parallel, as you go, maybe your first planner solves, let's say, 80%, and then as you keep adding planners, those planners really just have to address the failures of the first planner, right? And so you could even think about a planner as just outputting a single trajectory that addresses a single failure case or something. So, and so then when you get down to that level, it really almost turns like into a trajectory library, right? So there's some pretty interesting ways you can extend these ideas. So yeah, I went a little off topic here. So for moving pedestrians, I mean, in some sense, if something's moving or not moving, that doesn't really change the problem as much. It just means that you have to plan forward and have to have time in your reasoning. So let's go to the so first, so goals for this exercise are, first get set up with the toolbox, get familiar with the different planning algorithms, and then explore the concept of environment dependence for planning algorithms, and then we'll have the planning challenge. Usually for the planning challenge, we have some kind of prize, but you know, some kind of gummy bears or something like this, but I guess we'll not have that this year. Okay, so everybody's set up with the toolbox. Okay, cool. And so first step to do is to run init setup.m to set up the paths and compile the max files. And then so let's see. And then there are a couple of different folders in here. So global search has sampling and grid planners. Local search has implementation of trajectory optimization. Cost function implements some common cost functions. And then environment generation allows you to generate environments and save the environment a bunch of maps. So first step, let's try and run the different planning experiments, different algorithms, and you can kind of see also. So just one thing I want to mention is like this toolbox is really for you to not implement algorithms that you actually want to benchmark again. It's more for understanding the concepts. So you can, once you open, let's see which one is this. So this is, for example, the CHOMP example, right? So first you load environment, then you create the cost functions and derivatives. You create an initial guess, and then and then you have some the function surrogate cost functions for CHOMP. Set up the parameters, stopping conditions, and then here you actually do the optimization, and then you can visualize it. So we can, let's start with this one. Okay. Okay. And then, so then this is the example we had before. So this is what you get for CHOMP. So here you can see basically A star expanding, and students, it tries to expand some states before getting to the goal. So it's found the path. And then the last example is T star.
Basti,
Yes.
I have a question for the A star example.
Mm-hmm.
I think there is no randomness in the algorithm for A star. Sounds right?
There's no randomness, no.
Oh, okay, so when I run the example, I got totally different result as what you showed on the screen.
So I think, yes, and there's something committed in there that shouldn't be committed. Oh. So basically, what's I think committed is that the heuristics inflated, and I think maybe that's closer to what you got, right?
Oh yeah.
So what heuristic inflation does is it's essentially a non-admissible heuristic, but it can be a good way to get solutions quickly, right? So you might not find the optimal solution, but you'd find a solution quicker.
Yeah, okay.
So something you might also, that might be interesting to see here is that, you know, A star and RT star are quite related in this structure, right? So you have with on the RT star side, you essentially, the sampler we have is a uniform random sampler, and we just get a single sample every time to get a new vertex. While for A star, we basically, you know, we just pick a resolution, and then our sampler is, when we get the sample, we actually get the whole 2D grid at once, and then just search. While here, the search, since there's only one vertex, there isn't a search. We just basically connect to that sample. So, you know, so you can think about A star and RT star actually quite related, even though they seem like completely different algorithms. Okay, so let's, I'll let you think about these questions. You know, how do these different algorithms behave? What happens if you vary the parameters of the different algorithms? So you can saw those parameters are in those M files. You know, essentially what happens if you inflate the heuristic, and we can't discover this right now, right? Like we basically turned A star into weighted A star. So how do we turn RT star into RT?
You could set the radius multiplier to 0.
Yes, I think that should work. Let's see, if we just run this. So let me get the rewiring here somewhere. But okay, yeah, so let's try it with 0. That should work. Actually, I'm not sure. Let's see. It should work, but it might. One of the things it might mess up is you don't actually get the successors. But I guess it seems like it did work. Let's see. Okay, that's the successor function. Yeah, I think that works. Yeah. So if the radius, if you don't get any successor, you basically find the closest one. Okay. So that's how we turn RT star into RT. Okay, so next I'll kind of stop talking for a while, and then let you guys run this. So there's, before I do this, let me show you. So there's, in here are 3 different environments, environment 1, 2, and 3. So run the environments on the different, so you can do this here actually. So if you run compare planner environments, then you can run the 3 different planners on the 3 different environments. So why don't you do that and then kind of try to run the algorithms on this matrix and then like where do the algorithms work, where do they perform well, try to fill out that matrix and then let's give you guys 10 minutes to do that and then let's report back on what you found. Okay, everybody's done? Okay. So it sounds to me like we have some conflicting results here in the chat. So maybe let's see. So why don't you guys start and maybe explain what you got and what you think. Maybe Suresh, since you're first, do you want to start?
Yeah, I think some of the experiments, the planner just I think runs out of time. I think finding the path. Should we consider that, or should we let it plan to find something?
Well, so I mean, one of the things that's a little tricky is that everybody's computer is a little different.
Yes.
So, but we do want to kind of, the time aspect is important, right? Like in terms of what we do, time is important for us. So, why don't you just say what you got and what your interpretation of this is?
Okay. It seems like CHOMP, even if it finds for certain environments, I think some of that those are in collision, even if it says like has that. In terms of time, I think like CHOMP is running the fastest for me, and weighted A star is the slowest, just because like the environment is set up in such a way that it has to like explore, first go to the left and then come back right. So I think it doesn't have much room for exploration, and then RRT star is like in between those two in terms of time.
Okay. So let's see. Let me just kind of maybe.
I'm running the experiments again just to see if I get a different.
Right. So the first environment is really like a maze-like environment, right?
Yeah.
And then I'll just run it here for RT star. Then the second environment has. Oh, so it's running each one for each planner.
I think the second one is art. Yeah, you could switch that.
I'll just run one planner just so I can show different environments. So the first one is this maze with this kind of narrow passage here, right? So yeah. This is really kind of nice for CHOMP because it can kind of find this narrow passage and exploit this first order information that any of the other algorithms would have trouble with. So for RT star, it will be really unlikely that we'll find this narrow passage. For A star, depending if the resolution lines up, it might find a path through it, or if you're unlucky, you don't find a path through it. Then this is the classical kind of bug trap example, and so here CHOMP has a lot of trouble, right? Because it can't essentially bend the trajectory enough to make it around. And A star is in trouble because it essentially has to fill out all this bug trap before it kind of spills over into the right solution, while RT star can kind of escape this pretty quickly. Okay, let's see. So last one is essentially this kind of maze. I don't know if you already talked about this, and this is really nice for kind of an A-star-like planner. Okay, so so let's get to the interesting part. So so assumption so far: no dynamics, start goal, no changing environment, no time budget, real time. Just to kind of clarify. So this is, so let's go to the, get to the planning challenge. So to run the planning challenge, we'll have essentially a training. We'll not do 3D. We'll kind of keep it as 2D for this for now, just to kind of keep things simple. So the planning challenge will also be 2D. So for the planning challenge, we'll have a prize. So we'll have a $30 grand prize to use at your local restaurant. And so to run the challenge, you run here. So we'll have a training set and a test set. And I'll reveal the test set later. So wait, it's still running. Okay, 1 second. So here's the run planner challenge. So later you'll replace the train with the test, and then so there's visualize and not visualize. So when you're reporting the result, turn off visualize, please. But for debugging, it's probably better to visualize. And then also you can see here there's a time budget for the actual challenge, right? So it can be that you run out of time. And so then you can use at most 2 planning algorithms, and you can develop your own planning approach, and we'll release the test set in the last 10 minutes, and then report your score in this document. It's basically just a Google Doc, so just put your name and score down. So put your name, test score, training score, and then so let's get started on the planning challenge, and then and we'll come back. Let's say how much time do we have? Also, maybe we'll go a little over. Let's say maybe let's say 20 minutes. So let's come back in 20 minutes, and I'll give you the test set in the last 5 minutes. I think it should be enough to run. So I'll just start the timer. So so this is where you can find the test set. Please only use the test set once at the end. Don't run more than once on the test set. And then so this only at the end, run once on the test set. Please use the training set for development. And once you're done, you can report the numbers. So there's still 10 minutes, 45 seconds left. Okay, I'll just add a timer. Okay, and it's noon. So who won the challenge? Let's see. Okay. Congratulations, Brady. Cool, great. So Brady has won the grand prize of $30 for the next takeout. So we'll resume at 1 p.m.